There's a basic mistake in the picture most people have of the solar system. If you drew the sun in the center of a page and put Pluto at the edge, it would feel complete, but you'd be missing almost the entire structure. Because the planets aren't the main feature of our home, they're the crowded center. The real boundary is thousands of times farther out. It forms a giant shell around our star. It's called the Oort Cloud. And here's the strange part. We've never photographed it directly. Not a confirmed object, not a clear image. Yet we know it's there because it keeps sending us messengers. Those messengers are comets, and in a minute, I'll show you the evidence that forces astronomers to believe this shell exists. But first, you need to replace the usual solar system shape in your head. The planets mostly orbit in a flat plane, like a dinner plate. That's the diagram everyone knows. The Oort Cloud doesn't follow that shape. It isn't a ring, it isn't a belt, it's a sphere, a massive hollow bubble that surrounds the sun from every direction, above, below, and to the sides. And it's so big that it makes the planets look like dust. Astronomers measure distance in astronomical units. 1 AU is the Earth, sun distance, about 93 million miles. Neptune is about 30 AU away. That's the edge of the planetary neighborhood. But the Oort Cloud doesn't even start until thousands of AU from the sun, roughly 2,000 to 5,000 AU, and it may extend outward to tens of thousands of AU, around 50,000 to 100,000 AU. Here's a way to feel that. Shrink the solar system so Earth is 1 inch from the sun. Pluto is only a few feet away. You could fit the planets on a dining table. On that same scale, the Oort Cloud wouldn't begin until you walked hundreds of feet away, and its outer edge would be far beyond that. The whole solar system becomes a sphere that's miles wide, with the planets as tiny specks in the center. Now here's a detail most people get wrong. They imagine the Oort Cloud like a crowded minefield, like you'd have to dodge icy rocks if you flew through it. The reality is the opposite. It's emptier than you can picture. Even if it contains trillions of icy bodies, the space is so vast that the distance between objects can be tens of millions of miles. If you stood on one of those objects, you wouldn't see the others nearby. You'd see stars, and the sun wouldn't look like a sun. It would look like the brightest star in the sky. So if it's that empty, why does it matter? Because it's not a static wall, it's a fragile boundary, and fragile boundaries can be disturbed. A lot of people assume those icy bodies formed out there and stayed there, but the real story is messier. They likely formed much closer to the sun, in the same region where the giant planets were forming. Early on, the solar system wasn't stable. The big planets shifted, they migrated. And as they moved, their gravity acted like a slingshot. They scattered huge numbers of icy objects outward. Some were thrown so hard they escaped the solar system entirely, becoming interstellar wanderers, but many didn't quite get enough speed to leave. They traveled outward until they reached the weak edge of the sun's gravity and stalled. Over billions of years, two things helped shape that scattered debris into what we call the Oort Cloud. First, the gentle nudges from passing stars. And second, something even bigger, the Milky Way itself. This is where the solar system starts behaving differently. Near Earth, the sun's gravity dominates everything. Orbits feel predictable. The solar system feels like a closed arena. But out in the Oort Cloud, the sun's grip becomes weak enough that the galaxy gets a vote. Astronomers call this influence the galactic tide. Just like the moon raises tides in Earth's oceans, the mass of the Milky Way exerts a tidal pull on the outer solar system. It stretches and distorts the orbits of those faraway icy bodies, constantly competing with the sun's weaker pull. That's part of why the Oort Cloud isn't a flat disk like the planets. The galaxy helps keep it more spherical. But it also means the cloud is sensitive. It can be shaken. Stars move through the Milky Way, and sometimes one passes close enough to disturb our outer boundary. We can predict at least one future encounter like that. A star called Gliese 710 is currently tens of light years away. Calculations suggest that in about 1 million years, it may pass through the outer region of the Oort Cloud. That's not just a near miss, it's a direct disturbance of the shell. And when a star does that, it can scatter millions of comets. Many will be thrown out into deep space, but many will be knocked inward toward the inner solar system, creating a long comet shower that can last for millions of years. So the Oort Cloud isn't just a distant border, it's an active link between Earth and the motion of stars around us. Now let's come back to the uncomfortable fact. We've never seen it directly. So how can we possibly know it's there? The first problem is light. These objects don't glow, they only reflect sunlight. But at tens of thousands of AU, the sun is just a bright star. The light reaching a small icy object out there is extremely weak. Spotting one is like trying to see a tiny piece of coal against a black background from an impossible distance. You might think infrared would save us. Infrared sees heat, not light. But the objects in the Oort Cloud are incredibly cold, only a few degrees above absolute zero. That means they emit almost no infrared radiation. Their heat blends into the background of deep space. Distance, darkness, temperature, and contrast all work against us at the same time. So the Oort Cloud isn't proven by photography. It's proven by behavior. Specifically, the behavior of comets. Comets entering the inner solar system fall into two main groups. Short-period comets are the regulars. They orbit the sun in less than about 200 years. They tend to travel close to the same flat plane as the planets. Their source is the Kuiper Belt beyond Neptune, which we can observe. But long-period comets are different. Their orbits can take thousands, tens of thousands, or even hundreds of thousands of years, and they don't arrive neatly along the planetary plane. They come from steep angles, from above and below, from every direction. That pattern is the clue. If their source were a flat ring, they would mostly arrive along a flat plane. The fact that they arrive from all directions means the reservoir must surround us. It has to be a sphere. There's one more problem that makes this unavoidable: supply. Comets are fragile. Every time one passes near the sun, heat boils off ice and strips mass away. After enough passes, it breaks apart or goes dormant. If the solar system is billions of years old, the comets should have burned out long ago. But we still see fresh, long-period comets today. That means there must be a massive deep freeze reservoir far away, holding billions of potential comets, waiting until disturbances send a few inward to replace the ones that die. That reservoir is what we call the Oort Cloud. Now here's where a lot of people get fooled again. They hear interstellar space and assume it means outside the solar system. That's not always true. Take Voyager 1, the most famous spacecraft in history. Many people think Voyager left the solar system years ago. In 2012, headlines declared it had entered interstellar space. Technically, it crossed a boundary, but it wasn't the boundary most people imagine. There are different edges. One edge is magnetic. The sun blows a stream of charged particles called the solar wind. That wind creates a bubble around the planets called the heliosphere. The outer boundary of that bubble is the heliopause, where the solar wind's pressure balances the pressure of interstellar space. Voyager crossed the heliopause. It measured a drop in solar particles and a spike in cosmic rays. That's why it's said to be in interstellar space. But gravitationally, Voyager is still in the sun's territory. The solar system, in the deepest sense, is defined by gravity. It ends where the sun can no longer hold onto objects. By that definition, Voyager has barely left the front porch. Voyager is only a little over 100 AU from the sun. That sounds enormous until you compare it to the Oort Cloud. Voyager is in the empty gap between the heliopause and the inner edge of the Oort Cloud, and it won't reach the beginning of the cloud for centuries. Now here's the tragic part. Voyager's power source is fading. In the next few years, its final instruments will likely be shut down, and then it will fall silent. That means Voyager will become a dead piece of metal long before it ever reaches the Oort Cloud. And yet it will keep drifting outward anyway, silent and unseen, for thousands of years, eventually taking tens of thousands of years to cross the shell and truly pass beyond the sun's gravitational territory. This is why the edge of the solar system feels so strange. It's not a wall you crash into. The barrier is emptiness. In science fiction, ships often refuel by stopping at moons or asteroids, using local water to make propellant. That strategy, island hopping, is at least imaginable in the inner solar system because targets are relatively close together. But beyond Neptune, the islands disappear. The Oort Cloud may contain trillions of objects, but they're spread across such an enormous volume that the density is close to zero. The average distance between two objects can be comparable to distances between planets. You can't count on pit stops. You can't reliably refuel. You're entering a desert tens of thousands of AU wide. And that creates a brutal engineering reality. If you can't refuel, you must carry fuel from the start. But fuel adds mass. Mass requires more fuel. The requirement grows fast. With chemical rockets, crossing the Oort Cloud on a human timeline becomes close to impossible. A 30,000-year trip is not a mission. It's a geological event. So the Oort Cloud has a strange dual meaning. On one hand, it's a cradle. It defines the territory of our sun and holds pristine frozen material from the birth of the solar system, preserved for billions of years, waiting to be studied. On the other hand, it's a cage, not because it's dense, but because it's empty, a mode of distance that makes leaving our neighborhood far harder than most people realize. The Oort Cloud is the dark shoreline of our home, the place where the familiar solar system fades and the interstellar sea begins.